Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking right now at Chapter 8, Production of Power from Heat. And in particular, we're looking at the basic Rankine cycle for a steam power plant. And the idea here is that you have a pump which increases the pressure, sends the material to a boiler or a vaporizer. So you come out with high temperature and high pressure steam at state 3. And then that's going to be sent through an expander or a turbine that will produce work. So it's going to take that high energy steam and bring it out as low energy steam, which will be at a lower pressure and temperature. And then we need to return it to our initial feed to the pump state. So we're going to send it through a condenser to take this vapor and turn it back into a liquid, and then repeat the cycle with a pump. Now the idea was that the pump is going to bring in a liquid, typically a saturated liquid. We almost always assume that this is a saturated liquid, so quality is 0 at this point. P2 is going to be higher than P1. There's no heat transfer at the pump, but there will be work required by the pump, so work input to the system. The boiler or vaporizer is going to require heat transfer in, and we have to pay for that because that's going to be a fuel cost we pay for. And then I'm going to produce power in the turbine. The sum of the work for the pump and the work for the turbine will be my net work. And then I'll have heat loss in the condenser. We did an example in class of this, and I want to now talk about some of the things you might do to vary the cycle and what will happen if you do this. So the first one of these was, take a Rankine cycle problem and just work through it, okay? And then look at that and see if you can figure out what would happen if you lowered P4, P1, that pressure there, okay? Generally, we are assuming that our condenser is isobaric, so therefore those would be the same. Now what's going to happen is if I lower that pressure, then the material stays in the turbine longer, producing more work. So I will get more work out of this, but I also am going to have to pump up the liquid from a lower pressure to that same pressure. So it's going to require a little bit more work at the pump, but the net will still be an increase in work. It's not going to change the heat transfer at the boiler, but I'll have a little bit more heat transfer in the condenser. But this will, in fact, increase the thermal efficiency. But here's one problem, is that that's going to lower the quality coming out of the turbine, which destroys turbine blades. It will leave pits in them, which eventually just will totally eat away all the metal, and you don't get power out of the turbine anymore. This is very expensive. So generally what we do is we go to the lowest possible pressure so that X4, and this is the ideal X4, is greater than 90%. What's going to happen is that the actual, when I throw in process efficiencies, I need that to be more than 95%. Can I emphasize actual enough, writing it on both sides? But this is a good way to figure out what the lowest pressure could be. What if we were to superheat the steam in the boiler? Now, it's going to come out of the boiler at a higher temperature, the same pressure that we were talking about before, but a higher temperature, which means it has more enthalpy, more energy, okay? That's going to allow me to produce more work from the turbine. But I also am having to increase the amount of heat transfer. So this may or may not actually really help things. It will improve the Carnot or maximum for thermal efficiency, right? That would be 1 minus TL over TH. And if I have TH increasing, then 1 minus TL over TH is going to also, I'm going to subtract a smaller and smaller number, so that will improve my thermal efficiency maximum, but it might not improve the overall efficiency of the real cycle. But we do this sometimes not for the improved efficiency, but because we are protecting our turbine blades. We also could just increase the pressure at the boiler. Now this will mean I have to pump to a higher pressure, but I'm going to have more work I'm going to produce out of the turbine. Okay, again, net effect will be more net work. Okay, but when you do this, I'm going to warn you, if you had carefully designed the lower pressure, you're now going to have problems with the lower quality. At the exit of the turbine, that quality is going to probably drop below 90% if you were designing it to where it was very carefully sized. So be very careful on this and be sure to check the quality at the exit of the turbine. But there are some other things that you can do, and one of those is the reheat cycle. Because the problem is when I do those other simple modifications, I may improve the thermal efficiency, but those same things tend to hurt the quality out of the turbine, and so be expensive. Your boss doesn't like you because you're costing him yet another shutdown and more spare parts. And so one way to avoid this low X4 is to, before the material totally exits, send some of it and reheat it. So this is like splitting the turbine into, two phases. So I'll start with going from high to medium pressure. I'll take it out at that medium pressure, send it back into the boiler and reheat it. Out of there, I'll send it back into a low pressure. So I'll go from the medium pressure down to a low pressure turbine. And then I can finish the cycle from there. It's not going to improve the thermal efficiency, but it will protect my equipment. So this is what that picture might look like. So I start with it here as the feed to the pump. I'm going to bring it through the pump. I'm going to boil it. I'm going to send it into the turbine. But the difference is I'm going to have it come out early, be reheated, back into a turbine again, and out, and rejoin the cycle. And so this is done not as a way to improve efficiency, but this is done so that you protect your equipment by avoiding a low value for quality at the exit of your turbine. If you wish to analyze this, it's really not difficult. You know all the skills. All the heat transfer devices we're going to assume are constant pressure or isobaric. The boiler and the heater, we're going to heat them to a quality of 1, so saturated vapor, unless they specify something else. We're going to take the condenser and cool it to a quality of 0, saturated liquid. I'm going to assume that all my pumps and all of my turbines are reversible and adiabatic as the ideal, so isentropic. And the net is going to be the sum of the work at all of my turbines plus any pumps I need. So as many of those as you have, you just can simply add them together. And the heat transfer at the boiler is the sum of all of my heat input devices, so the boiler and the reheat section. So I'll have 2 pieces of that, making the calculation slightly more complex, but there's no additional knowledge needed. One way that we can make the cycle more closely approach the maximum or Carnot efficiency is to preheat the fluid before it goes into the boiler, so I don't have to use as much fuel. And the way we do this is with a FEEDWATER heater. Now you can do this with 2 types of FEEDWATER heaters. You can have an open FEEDWATER heater or a closed FEEDWATER heater. The open FEEDWATER heater is the least expensive, and what it is essentially a mixer. You bring in 2 fluids, you put them into a box where they are allowed to mix, and one fluid comes out at kind of the average, the weighted average of those energies. To analyze this, I know that the sum of the Q in is going to equal the sum of the Q out. Typically, we have one stream out and two streams in. For a closed feedwater heater, I'm going to do those as a heat exchanger. So one stream will go in and out at one temperature, and the other will go in and out at a different temperature or different pressure and temperatures too. And the heat will transfer between these two streams. So this just is a heat exchanger. And again, the sum of the heat transfer in is equal to the sum of the heat transfer out. This is what an open feedwater heater system might look like. So I begin with my pump, and I'm going to bring it up to some intermediate pressure. I'm going to mix it with some material that I've withdrawn early from the turbine at the same pressure, and that's critical that P6 has to equal P2, and that then tells me what P3 is going to be. Then I'll pump it all the way up to the high pressure, run it through my boiler, but it's not going to require so much heat because it's already warmer than it would have been without this feedwater heater. Then I'm going to run it through the turbine. The difference here is that now then my turbine has two exit streams. So the work is going to be the sum of m dot times the enthalpy out minus m dot enthalpy in for all my streams. In this case, I have one stream in, but two streams, 6 and 7, coming out. Again, then, I finish by running it through a condenser. Here's a summary page of the equations that you'll need. Now, this does require you to do mass balances at the places where I have my streams splitting or combining. So I need to do mass balances at two positions, but the mass flow rate through this end is all the same, and the mass flow rate through this end is all the same. It's just that this mass flow rate is not the same as that mass flow rate. You can calculate the work, you can do energy balances on that feedwater heater, and all of those are shown here. This is a sample of what a closed feedwater heater system might look like. So in this case, I'm going to bring it from a pump, but I'm going to bring in a heat exchanger so that I can preheat the material. Now, typically what we do, and it's probably easier to look at it starting here. So I'm going to feed through the boiler and I'm going to heat the stuff up. I'm going to run it through a turbine, but I'm going to take it out early, and I'm going to take the fluid out early. Some of it will continue on to the rest of the turbine. Some of it's going to come over here to do the preheating. At this pressure here, now this pressure is kind of a mid-range pressure, and it's going to go on to the lower pressure turbine to the lowest pressure. So it's at its high point here, and now it's at a midpoint. So this one portion is going to come over here into the heat exchanger and go on and be pumped up to the high pressure. And this material is going to be pumped, and we're going to go ahead and just pump it directly to the high pressure. So this is going to go from low to high. This one is going to go from mid-range to high. In the mixing box, I have to operate at a constant pressure, so everything needs to be at that same high pressure. We'll leave from there, go to the boiler. So the part that didn't get sent back for the feedwater heater is going to go onto the turbine, continue doing work, and will then be fed back to the condenser to be regenerated into a liquid. You are going to have to do mass balances at the places where it gets complicated. So this split point and the mixing point are the two places where material balances are required. There's an example in the book that I really recommend you look at. It's a much more complicated example, but kind of a similar concept, that they are taking out side streams at various points as the pressure drops in the turbine. Only one portion of it is actually going to go all the way through, run through the pump, and so forth. The rest of it is going to be used as a preheater, and you can follow the math of this one in your textbook. So this concludes our kind of review of variations on Rankine cycles. And next we will be looking at a gas variation on this called the Brayton cycle. Thank you very much for your time.